boys. Good morning to all of you. Today I am going to start a new chapter, ordination compounds. As you know, this chapter is belonging to inorganic chemistry, and it is a very important chapter in order to understand the inorganic compounds, especially coordinate compounds, complex compounds. Here you see that coordination compounds means the compounds in which the metal atom is bonded with other species through coordinate bonding. Let us take an example of a coordination compound. This is an example of coordination compounds. Here NH3, 4, Cl2, square bracket, Cl. Look at these coordination compounds. If you look at the coordination compound, there is a coordination sphere. Within this coordination sphere, there is a central metal atom. This can be atom or ion. There are 4 molecules of ammonia, 2 chlorine, and outside there is a chlorine. This compound is a coordination compound. It is, if you draw the shape of this compound, structure of this compound, you will see that this compound is octahedral in shape. The coordination sphere. There are 4 ammonia molecules, NH3, NH3, and 2 chloride ion, Cl minus, Cl minus. This is the shape of this part, and you can write it this way. Octahedral entity, outside there is chlorine, this is positively charged, this is negatively charged. Now if you see the bonding, here is ammonia molecules bonded to chromium through coordinate bond with the help of lone pair of nitrogen. This is the lone pair of nitrogen, this is the lone pair of nitrogen. And in Cl minus there are 4 electron pairs, 1, 2, 3, 4, 1, 2, 3, 4. The Cl minus ions, chloride ions, are also bonded to the chromium central metal through coordinate linkages. So the entire bonding inside the coordination sphere, coordinate bonding. Here you see that there are 2 types of bonding present here. One is chromium. Chromium is bonded to Cl minus through a coordinate bond as well as through an ionic bond. This here Cl is also bonded to the Cl minus through a coordinate bond as well as through an ionic bond. And here is the Cl minus outside the coordination sphere. This Cl minus is bonded to the central metal chromium through an ionic bond. So if you understand, if you look at the entire figure, you will have 2 types of bonding. One is coordinate bonding and another is ionic bonding. This coordinate bonding, number of coordinate bonds of chromium central metal, this is known as the secondary valency. And the ionic bonding with the central metal chromium is ionic bondings are known as primary valency. So if you count the secondary valencies, you will see there are 6 secondary valencies because there are 6 coordinate bonds. So the secondary valency is equal to 6, and primary valency, that is ionic bonding 1, 2 and 3, primary valency is 3. Secondary valency 6 and primary valency 3. Now here you see that secondary valency, what it does mean? It means that the central metal atom or ion is bonded to some molecules, neutral molecules or anionic species through coordinate linkages. This number of coordinate linkages is called secondary valency. And the central metal ion or atom, here the central metal chromium has 3+ charge. It's an ion because you see that here total negative charge is 2 minus, 1 minus, 3 minus. So the oxidation number of chromium is class 3. So if you look at the oxidation number, chromium, central metal, it is central metal. The metal which is present within the coordination sphere is known as central metal. The oxidation number of the central metal is class 3. So class 3, this valency is satisfied by 3 chloride ions. Out of the 3 chloride ions, 2 chloride ions are inside the coordination sphere and 1 chloride ion is outside the coordination sphere. Now the second primary valency, that is chromium with 3 positive charges. The positive charges, 1 positive charge satisfied by 1 chlorine minus, another positive charge satisfied by another chlorine minus, and another positive charge is satisfied by another chlorine minus. So primary valencies are satisfied by anionic species. Primary valency of the central metal generally satisfied by the anionic species. And secondary valency, that is the number of coordinate bonds. Number of coordinate bonds 1, 2, 3, 4, 5, 6. These valencies are satisfied by neutral molecules or anionic species. Now the question is that the secondary valencies are satisfied by the neutral molecules and the anionic species. These are together known as ligands. Therefore, these ammonia molecules, 4 molecules of ammonia and 2 chloride ions, these are acting as ligands. So what are ligands? Ligands are the neutral molecules or anionic species which can satisfy the secondary valency of the central metal atom or ion. I am repeatedly telling that in many cases you will see the central metal has 0 oxidation state, and if the central metal has 0 oxidation state, it is an atom, simply an atom. And if the central metal has positive oxidation state, say +1, +2, +3 like this, we say central metal ion. That's why we tell that central metal atom or ion. Repeatedly we say central metal atom or ion, because in many coordination compounds the central metal may be present at 0 oxidation state, in that case it is atom, and in many coordination compounds the central metal has positive oxidation state, and in that case it is ion. Now we see that here in this coordination compound, chromium 3 plus is the central metal ion, 4 ammonia molecules acting as ligands, and 2 chloride ions also acting as ligands. So you see the role of 2 chloride ions which are inside the coordination sphere. These chloride ions are satisfying the secondary valency as well as primary valency. So this is happened in case of anionic ligands. The anionic ligands simultaneously satisfy the secondary valencies as well as primary valency. Now the question is that if you summarize it, we say that secondary valency of the central metal, this is called coordination number. Coordination number, in short it is written as Cn, coordination number. Coordination number equals to secondary valency. Coordination number of the central metal atom or ion is equal to its secondary valency. So coordination number is 6. And primary valency, this is equal to oxidation number of the central metal. So primary valency equals to oxidation number. Oxidation number. So primary valency equals to oxidation number and secondary valency equals to coordination number. This primary valency 3, we write 3. It may be positive, and some cases, very few cases, the primary valency may also be negative. So remember, the central metal can have the primary valency with negative oxidation number also. This is also possible, but the cases are very few, very rare. So we are not writing any sign here. Oxidation number equals to primary valency, and you can write the primary valency class 3 or simply 3 as you like. discuss again that these primary valencies are normally ionizable, but not necessarily be. Primary valencies are normally ionizable and secondary valencies are non-ionizable. These two things you must keep it in your mind, that secondary valencies are not ionizable, non-ionizable, and primary valencies are normally ionizable, means they can ionize. Say in this case, if we dissolve this compound in water, ionization will take place. So when it will ionize, this primary valency, which is only attached to primary valency, this primary valency will ionize. This will ionize. But this will, Cl minus will be separated from it in the form of ions. And the entire ordination compound, entire ordination sphere with positive charge will be the cation. This primary valency and this primary valency will not ionize. So which primary valencies are ionizable? Those primary valencies are ionizable which are attached to the central metal ion through primary valency only, and which are non-ionizable, the primary valencies which are non-ionizable, which are simultaneously attached with secondary valency. तो remember, जो प्राइमरी वैलेंसी से ही अटैच्ड है और कोई वैलेंसी से अटैच नहीं है, वो प्राइमरी वैलेंसी आयोनाइजेबल है। जो प्राइमरी वैलेंसी सेकेंडरी वैलेंसी के साथ अटैच्ड है, दोनों के साथ अटैच्ड है, वो आयोनाइजेबल नहीं है। दिस मीन्स इफ यू पुट दिस कॉम्प्लेक्स इन वाटर class aqueous, this will ionize in this way, that if you write this whole thing Cr NH3 whole 4 Cl2, this entity and this entity, only this will be ionized, plus aqueous plus Cl minus aqueous. So see the ionization. Look at the ionization. If it is dissolved in water, this will be the cation and this will be the anion. So it is clear that only this primary valency is ionizable. The other primary valencies are not ionizable, and that's why it is told in the Warner's theory that central metal in a coordination compound possesses two types of valencies, and these are primary valencies and secondary valencies. The second point is the primary valencies are normally ionizable and are satisfied by negatively charged species or anions. The primary valencies are normally ionizable, means not necessarily be, and are satisfied by negatively charged species or anions. Third point, the secondary valencies are non-ionizable and are satisfied by neutral molecules or anionic species known as ligands. So see, third point, it is told in the Warner's theory that secondary valencies are non-ionizable and are satisfied by the neutral molecules and anionic species known as ligands. Now, I am telling an experimental fact here. So, the experimental fact is that if this coordination compound is dissolved in water, if you take this coordination compound, 1 mole of this coordination compound, and if you 1 mole of this coordination compound here, NH3 whole 4 Cl2 Cl plus excess of silver nitrate. This means what? It is a chemical proof that 1 mole of this is taken and excess of silver nitrate is added to it. We get 1 mole of AgCl. So see, this fact clearly indicates that the ionization, only 1 mole of Cl minus ions are ionized. 1 mole of this is taken, excess of silver nitrate is added, and what we got? 1 mole silver chloride. So 1 mole silver chloride means what? that 1 mole silver chloride means this, that only 1 mole Cl minus ions have been ionized from 1 mole of this ordination compound. So it is clear that outside there is only 1 chlorine. This outside chlorine is completely separated after ionization. This is called counter ion. So this is counter ion. What is the counter ion? Counter ion is here Cl minus. Counter ion. Cl minus is the counter ion of these coordination compounds. Now see these coordination compounds, if you see different types of ligands are attached to the central metal, atom or ion. The coordination compound is called heteroleptic coordination compound. So this is an example of heteroleptic coordination compound. Heteroleptic coordination compound. When do you say heteroleptic? When the metal, central metal is attached to the ligands, different types of ligands, then it is said to be heteroleptic. If the central metal atom or ion is attached to same type of ligands, same kind of ligands, then it is said to be homoleptic. So heteroleptic and homoleptic, these two things make it clear depending upon the types of ligands attached to central metal atom or ion. When the ligands are different kinds of ligands are attached, then it is heteroleptic. Same kind of ligands are attached, it is homoleptic. You will get many examples of this one. Now I come to the next topic, that is ionization. You understood this coordination number, you understood oxidation number, you understood oxidation number equals to primary valency, coordination number equals to secondary valency. You understood how does it ionize, which primary valencies are ionized, which are not ionized in water, in aqueous medium or in molten state. These things you have ionized. The coordination sphere and the ligands, central metal, atom or ion, all these things you have understood. Now we want to say something about ligands. So what is ligand? First question will come, what do you mean by ligand? Ligand is the neutral molecule or anionic species which can bind to the central metal atom or ion through secondary valencies, through coordinate bonding. They are called ligands. Now, ligands on the basis of their donor site, number of donor site. Ligands are classified as unidentate ligand, bidentate ligand, tridentate ligand, and so on, polydentate ligands. So, on the basis of their number of donor site, see ammonia, it has only one donor site. So, ammonia is unidentate, sometimes it is called monodentate. So, ammonia is unidentate ligand. Cl minus is also unidentate ligand because it is making only one coordinate bond. Remember, if an atom has more than one lone pairs, it can form only one coordinate bond, irrespective to the number of lone pairs. Remember it. कितना भी lone pair किसी atom में हो, वो सिर्फ एक ही coordinate bond बना सकता है. So it is, make it clear. Never confuse with this that there are 4 lone pairs, so it can form 4 coordinate bonds. Not like this. An atom can form only one coordinate bond irrespective to the number of lone pairs present on it. Now, ligands we are telling that unidentate, bidentate, tridentate, polydentate. So let us see some examples of such ligands. Monodentate ligands. Monodentate ligands, their numbers are many. Unidentate ligands, their numbers are many. Means we have a number of unidentate ligands. Bidentate few, tridentate few, tetradentate few ligands are there. So what is necessary for you? You must remember, you must know the ligands which are bidentate, tridentate like this. Monodentate, many monodentate ligands like ammonia, neutral, water, these are neutral, amides, Cl minus, unidentate. These are anionic ligands. And sulfate, though it carries two negative charges, carbonate carry two negative charges, but they are unidentate. Only one coordinate bond can be formed from oxygen minus side. Remember, the another oxygen minus side will not form because of resonance. So sulfate, carbonate, these are having two negatively charged oxygen atoms, different oxygen atoms, but they can form only one coordinate bond because of resonance. And some other examples like what we say OH minus, you can say halide ions, sulfate ions, nitrate ions, NO3 minus, nitrate. These are the examples of unidentate ligands. So these are all the examples of unidentate. What does it mean? Means they can form only one coordinate bond with the central metal atom or ion. These are unidentate ligands, and the number of unidentate ligands are many. You will get more examples there. Out of these unidentate ligands, look at these three ligands. These three ligands, NO2 minus, Cl minus, HCl minus. These ligands have two donor sites. See Cl minus, this is the bonding of Cl minus. Cl minus bonding, this is the bonding of NO2 minus. NO2 minus. So what I say that sometimes bonding may take place through nitrogen, bonding may take place through carbon, but not simultaneously. When Cl minus bonded to the central metal through nitrogen, then it is written as NC. And when Cl minus bonded to the central metal through carbon, then it is written as Cl. This is the difference. So Cl minus is a ligand, it is a unidentate ligand, but it can attach, it can link to the central metal through nitrogen side as well as through carbon side. But whenever it will link, it will always link with one of the other side. ऐसा नहीं तो इधर से भी लिंक हो रहा है, इधर से भी लिंक हो रहा है साइमल्टेनियसली, ऐसा नहीं. जब भी होगा नाइट्रोजन साइड से होगा, नहीं तो कार्बन के साइड से होगा. Such ligands are known as ambidentate ligands. Ambidentate ligands. We have a unidentate ligands. Out of the unidentate ligands, there are three such unidentate ligands which are known as ambidentate ligands. Means cyanide Cl minus or NC minus. Similarly, it can form coordinate bonding through oxygen side as well as it can form coordinate bonding through nitrogen side. Here is a lone pair. When nitrogen donates its lone pair for bonding, then it is written as NO2 minus. And when oxygen donates its lone pair for bonding, then it is written as ONO minus. So this is, remember, because you have to classify, you have to make it clear from which side, which atom, which donor side is used in bonding. If we write NO2 minus, that means the bonding takes place through nitrogen. If you write ONO minus, that means the bonding atom, donor atom is oxygen minus. So names are also different, and that's why we use different names. When it is NC minus, isocyano. When it is Cl minus, cyano. So from the name it is clear, cyano, isocyano. In the name, if I say isocyano, that means the bonding takes place through nitrogen side. If I say cyano, then that means the bonding takes place through carbon side. And if I say NO2, this one, bonding takes place through nitrogen side, it is nitrito-O, it is clear that the bonding takes place through oxygen minus side. And if it is given nitrito-N, this means it is clear the bonding takes place through nitrogen side. Nitrogen side, this side. Similarly, SCN minus thiocyanate, SCN minus thiocyanate, and NCS minus is isothiocyanate. So when bonding takes place through sulfur, then it is thiocyanate. When the bonding takes place through nitrogen, then it is isothiocyanate. And similarly, while writing the formulas, if we write HCl, you will understand thiocyanate. If we write NCS, you will understand isothiocyanate. If we write Cl, you will understand it is cyano. If we write NC, you will understand it is isocyanate. If we write NO2, you will understand it is nitrito-N. If we write ONO, you will understand it is nitrito-O. So these are the ambident ligands. So what are ambident ligands? The unidentate ligands which can use more than one donor site for bonding with the central metal atom or ion through coordinate bonds. The monodentate, unidentate ligands, you must say unidentate ligands which can bind to the central metal atom through more than one donor sites. Understand it, for coordinate bonding. This is our first video. You have seen the examples of unidentate ligands. In the next video, we shall talk about polydentate ligands, bidentate, tridentate, polydentate ligands, and some more types of ligands which are in your syllabus. Okay, boys? Thank you.